So and it's one major reading. It's a joint paper with, yeah, I do, with Tim Hubbard, Matt Gentry, and Dennis Nekopolov. There's some code. It's a bit dated from a book I wrote with Han Hong. It's in the appendices of this book. And then if you're interested, or if you're not experienced with implementing numerical methods, you can try this book with Golub and myself. So this, from my perspective, the big success story in the latter part of the 20th century was the systematic investigation of incomplete information. And for example, moral hazard, like Bob talked about, or adverse selection in markets such as auctions. And this was developed in tandem with game theory. And an important byproduct of that research program was the general specification of these problems as mechanism design, and then market design is kind of a subfield of that. These theoretical models are particularly compelling to econometricians because they provide alternative explanations for observed heterogeneity in data, rather not ones like measurement error or productivity shocks. And in fact, in auctions, measurement error is non-existent. They're typically contract data and they're exact. What happens when agents have private information and interacts in equilibrium is you can get really new phenomena. The most common is in IO. It's the big problem that almost all of us study is, how to sell a good. And in these situations, historically, there's been an asymmetry of information. The seller knows how much it cost him to produce this, but he doesn't know what the buyers are willing to offer. And similarly, the buyers don't know necessarily what their competitors are willing to offer. And so this sort of asymmetry information is common throughout markets. And so the idea is, well, how should you sell an object? Well, historically, the way to do it was to quote, take it or leave it price. This is actually quite a new idea. It dates to a man apparently named Wanamaker who lived in Philadelphia in the 19th century. Most selling occurred using pairwise negotiation. And a third option is an auction. The point is that there are a set of mechanisms, and depending on your objective, you may want to choose an auction or something else. And what determines the choice, obviously, in the first order depends on what your objective is, but it'll depend on other things as well. And the example I want to give is from George Washington, who before he became a general and a president was a surveyor, and he lived in 18th century Virginia. And this author Winship tells this story about one of Washington's friends dying and his becoming the executor of the estate. And this particular Virginian was like all the other ones, pretty land rich, but cash poor. And when he passed away, he couldn't cover his debts. And so what was common at the time was to sell the livestock, which also included slaves. And it was often done at auction. And Washington chose an alternative mechanism, a raffle or a lottery. And why would you choose such an option? And to most economists, that's kind of like backward. But in 18th century Virginia, distance was a tyrant, and there wasn't a lot of information. And so participation rates at auctions, even if they were advertised, were very small, low. And what we know about multi-unit or multi-object auctions are that they're highly susceptible to collusion. And also, Virginians didn't have a lot of money. They were cash poor and couldn't buy large assets. So why a raffle? Well, raffles, if they're reasonably priced, are affordable by lots of people, and people wanted to have a little flutter. And what Washington discovered was that the participation rates were extremely high at this raffle, and he made, you know, considerable money for the estate. Now the question to ask is, well, you know, what would have happened if he'd had an auction? And that's really kind of what the structural econometrics of auctions is about in one sense, is you get to observe one phenomena, and then using that information, what you'd like to know is, can you design a better mechanism? And what would the form of that mechanism be? And central to that is a particular object. It's I'm going to call it F of V. It's the distribution of valuations. So in the theory of mechanism design, there are typically kind of two agents, right? There's principals like sellers at auction and agents, potential buyers. And these folks have very different incentives. And what the mechanism design, market design literature proposes is that the principal gets to choose the rules with some objective in mind, and then he does that knowing full well that the agents are going to try to thwart him. And so the auction that John talked about yesterday, where there was incredible amounts of communication at these Korean car auctions, the designer obviously was going to shut that down. Maybe he got a little carried away, but there's no communication by construction virtually. But first, perhaps, I mean, folks who know this literature much better than I do claim, Larry Ausubel in particular, that Milton Friedman was perhaps the first economist to discuss market design seriously in a book called The Program for Monetary Stability, which was published in the 1960s. And in that, Friedman focused on how best to sell treasury bills at sealed bid auctions. And he discussed kind of two different phenomena at the time. One was a pay your bid. So everybody paid what they tendered. And the second was a common price, typically determined by the highest losing bid. And Ali Hurtacz studied something like this with treasury bill auctions in his dissertation back in the early part of the 2000s. In response to that, William Vickery investigated, was the first to investigate different auction formats and pricing rules within a particular informational paradigm, which is referred to in the literature as independent private values. Now, kind of the interesting thing about studying auctions is they're not new. They're extremely old. They're not as old as some other phenomena like money. In fact, you couldn't really have auctions without money, but they are thousands of years old, and which suggests that they're pretty durable. They're like the shark. They've survived a lot in evolution. But the main feature of them is this asymmetry of information. And because the seller and the buyer don't have this, there's this problem with getting the seller trying to get the buyer to elicit that information, to reveal that information. And but the main role that economists focus on in auctions is how well do they allocate goods for sale, and what kind of prices do they discover, and those are the kind of the main roles. So when I talk about these valuations, it's in a kind of a pretty nebulous way, right? And economists are kind of vague on where valuations come from. Usually in these models, they're an independent draw from an earn, and that's it. Usually people demand 1 unit, and that's it. So the one draw for that 1 unit is that person's marginal utility, and things like the budget constraint and substitution are largely ignored, which is a kind of a curious model of demand for economists. But that's the bare bones. And the Workhorse model is due to Vickery in '61. And it has an earn, big F of V, which has a corresponding PDF. Vickery studies something that's uniform, but you don't necessarily have to do that. And this model, where n people each get a draw from this urn, is referred to as the symmetric independent private values, because before the draw, everybody's essentially identical. There are other models in which there are different urns, and people get independent draws from that, and people refer to that as the asymmetric independent private values. Then there are models which bind these CDFs together, say by a copula, and impose considerable structure on that copula, namely a property known as affiliation, which in mathematics they refer to as multivariate total positivity of order 2. And that's called an affiliated private values. So there's a nest of these models, a class of these models, and this is the baby one. And it probably makes up 3/4 of the literature. So you got these n draws, and you can order them from largest to smallest. This is what this notation in braces or parentheses as a subscript. So the first highest order statistic, the second, the nth, and then the smallest. And in 9, we could draft these, as a step demand function. And what you see here is a demand function for n folks. And where you put the supply curve is in some sense going to determine what the transfer price is. So if you have 3 goods, or let's do 2 because there's a 2 there, then the transfer price will be something like between V3:n and V2:n. Okay, so a function related to f of v, using a term coined from the duration literature is the survivor function, where the CDF is the proportion of the population less than some value, the survival function is the proportion greater than that value. And so it's obviously related to the CDF according to this formula. And this survivor function is really the object of interest to people who do auctions, whether they know it or not. This survivor function is essentially the demand function. So when you make an assumption about f of v, you've made it an assumption about s, and you've made it a function about demand. And how is that? Well, imagine that you have a population of n potential buyers, consumers, and each of them have the draw from the urn. What is the equivalent of demand? Well, it's what we plotted. What about expected demand? Well, for any price P, the fraction of the population who would purchase is SV of P. And everyone wants at most 1 unit, and there's n of them, and they're independent. So the expected demand is just n times the survivor function. And so we can plot that thing just like this. And the object in the work in if you knew those valuations for whatever reason, then you could use something like the empirical survivor function, say a Kaplan-Meier product limit estimator, to estimate S of V using S of hat. And then you could use that in lieu of S of V, because typically S of V is not known. And so the object would be to see how close you could get your estimator S hat, which is this step function, to the dashed line, which is the expected one. Okay, so the problem is that most folks don't bid their valuation. They bid something different from it, or they potentially can. And different auction formats, open outcry versus sealed bid, and different pricing rules, pay your bid versus second price, provide buyers with these different incentives concerning how to bid. Consider pay your bid auctions determines what, consider the pay your bid rule. A bidder's action, his bid determines what he pays. Whereas at a second price auction, the action of his nearest rival determines what he pays. And so when your action influences what is you have to pay, it's fairly intuitive that you would shave your bid. And the question is how much. The basic point though is that in equilibrium, the bid functions map the private information, their values into their actions in different ways. And we'll see later on how different that can be. Let's just try to train our intuition by examining an oral open outcry auction that can be conducted in one of two ways. The first is just to set the price very low and let it rise more or less continuously. This is our standard notion of an auction, often referred to in English auction. And the price rises, and as it rises, people are going to drop out when it surpasses what it's worth to them. And eventually there's just going to be two guys left. And when the second to the last person drops out, there's no incentive for the remaining bidder to continue to bid. And so he pays that price. So at an English auction, you would pay V2:n, the second highest price. V2:n is a pretty compelling number to economists. It's the value of the object in its next best alternative use, also known as the opportunity cost. So you can see why some price set at auctions are very compelling to economists because they have a very specific meaning. So what you want to do, if you can, is use the observed bids at auctions to appropriately transform to estimate this survivor function. And then once you have this survivor function, you can use this for any sort of policy analysis that you might like. As a technical aside, within the IPV model, the equilibrium at an English auction has a special structure. It's a weakly dominant strategy to reveal your type, to tell the truth. As the standard way that economists model oral auctions is as clocks. This is due to Milgram, perhaps, and others. And basically, they imagine a clock either with a panel or just an analog clock, and the price rises and people drop out at various parts. And as I mentioned, in the absence of bid increments, it's the second highest bid, and that has this very attractive feature. Namely, it's the opportunity cost. The second way you could have an oral auction is to have the price start extremely high, say at infinity, and then drop and wait until someone would enter the auction. And the first person who cries out wins, and he pays that bid. These are implemented with clocks typically, and often to sell fish and flowers in the Netherlands. And for that reason, they're often called Dutch auctions. The strategy at a Dutch auction is quite different from that at an English auction, because the price the winner pays is related to his action. When he cries out, he has an incentive to shave his bid, to wait longer before pushing the button or stopping the clock. And in theoretical models of Dutch auctions within this IPV model, the equilibrium is not dominant strategy. It's something stronger called Bayes-Nash. And in a Bayes-Nash equilibrium, the person shades his bid. And the amount he shades his bid depends on his valuation, the amount of competition, the reserve price, the minimum price that must be bid, as well as the shape of the distribution of valuations F of V. But the important thing to note is that the person who bids first is the person with the highest valuation. And so as with the English auction, the object is allocated efficiently. And so this is a particular compelling feature and why folks like auctions, because under these valuation assumptions, they will allocate the good efficiently. Economic theorists have studied this mechanisms a lot, and they found that, you know, what really matters in auction design is first and foremost the type of asymmetric information. Is it private value or is it common value? The common value is what you might think of in oil, namely where we all have different beliefs about how much oil, whether there's oil or how much oil there is in a particular play, but none of us actually know until someone has drilled the hole. And then to a first approximation, that oil has the same value to all of us. Those auctions, common value auctions, are more about price discovery than they are about allocation, right? Since it's worth the same to all of us, we could just use a big die to determine who gets the oil. The reason to have an auction is to know how to divide up that pie between the seller and the buyers. But there's no efficiency issue in a common value auction because everybody has the same value. So what's important in common value auctions is price discovery. Typically, what's important in private value auctions is allocation. And so in environments in private values where the high bidder, highest valuation person doesn't win the auction, you're worried. And that can happen particularly in this asymmetric model of different urns. What's perhaps striking is
there's a question online here, whether it's possible to identify the impact of exogenous factors, for example, the auction environment or overall market trend on auction outcomes.
Yeah, so one of the things you would like to understand is how exogenous factors might influence the way you construct an auction. And so, you know, here I've got this very sterile environment where there's an urn, but you could imagine the urn being different in different environments. And because of that, how you would set up the rules would matter. And that's in fact what market design is about, is that not all environments are the same. And so you would want to craft or bespoke build a market for a particular environment.
Another question is, if agents do not be irrational in an auction, what is the general data requirement that guarantees such identification of irrationality?
Well, I mean, folks in experience, what's irrational? So some of us have done experiments, and to me, rationality is when they bid more than it's worth. Right. And so how can that happen? Well, in experiments, you randomly give them these chits, and these chits are replaceable with money, and they will bid for, you know, their chit will say $5 and they'll bid $7. And so you can say they're irrational or they're just messing with you, right? Because they're typically undergraduates who don't have anything better to do.
Or they get a warm glow from winning, just the sheer act of winning.
Sure. It's not like so Dave Krebs at the GSB, when he taught economics, used to bring in a jar of pennies and he would sell it to the class, right? And inevitably the person who won the jar would have paid too much for the pennies in the jar. That's not irrational, you know, that can happen. You guessed, you figured out how big a penny is and how big that jar is, and you made a mistake, and so you paid a little more for it than there is. I don't view that as irrationality. In the work that John will show you later, we have bidders that do things that look totally insane. What does that mean? They will go, I bid $10,000, now I bid $0. and then I bid $3,000, and then I bid $2,000. Those are ruled out by the rules of the game. But I don't view that as irrational, although Sunjin and John do. How can this be rational? Well, whenever someone builds a piece of software, it has seams in it. And if you don't have a good team of testers, you might let those seams go through. And so what do? Well, you do really weird things to see if you can break the software. Often when you break software, it'll pop you into a debugger, and then you can do all sorts of nefarious things. So I don't necessarily think that sort of behavior is even irrational. Right? Rationality is relative to an objective function, right? There's no empirical content to the hypothesis of optimization, which is a little disappointing, which is why we have to impose functional form on objectives. And then obviously people might not follow objectives. But anyways, I don't know if that answered the question. Went on for a while. Anyway, so one of the interesting things that comes out of this very sparse model is that if you were to sell the same good under two different institutions, the average winning bid at an English auction would equal the average winning bid at a Dutch auction. On the surface, that seems somewhat surprising until you realize that even though these environments reveal different amounts of information, to wit, the Dutch auction reveals no information until the winner is determined, whereas a huge amount of information is revealed as losers drop out of the auction. The fact of the matter is, in this model, knowing that Nikhil values something $10 does nothing to my valuation. Mine's still 7. I don't learn anything about Nikhil's valuation by his revealing it. If you want to have learning in an auction, or if learning is an important phenomenon, the valuations of the potential bidders have to be linked somehow. In the pure extreme, it's the common value. The thing has the same value to all of us. We just don't know it. In a weaker environment, there has to be some value in my knowing what Nikhil's value is. And it can't just be simple correlation. In fact, there are 9 versions of dependence, and it has to be the most extreme form of dependence, which is referred to as multivariate total positivity of order 2. And that essentially makes the joint distributions unimodal, and there's a very strong prediction on how their conditional expectations are related to one another. And so the basic point is, once you realize that you have the highest valuation, then all you need to bid on average is the second highest one. And in fact, that's what the bid function at a Dutch auction is. You bid, you say, I'm the highest value guy. How much would on average, given my valuation, how much would my nearest opponent, what's his valuation? And the bid function is exactly that valuation.
Harry, we have a question comes in from Zula. Which auction format will have the larger variance in winning bids?
We'll come to that. As you can see, the bid function for the English auction is a line. So the variance of bids is going to be the variance of valuations. The Dutch auction has a slope less than 1. So let's take a first approximation and call it a constant gamma that's less than 1. So the variance at a Dutch auction is going to be gamma squared times the variance of V. It's going to be significantly smaller. Notice too that, people lie. This is not news, right? But the winners lie the most. So what you know about a winner of a Dutch auction is he's a big liar. So you can do this for sealed formats, and theorists have, And what you find is there's kind of an equivalence. The first price sealed bid auction is strategically equivalent to the Dutch auction. And so there's a Bayes-Nash equilibrium there. And the second price sealed bid auction, often referred to as the Vickery auction in honor of William Vickery, is strategically equivalent to the English auction. And the dominant strategy is to bridge your type. And then there's just this revenue equivalent. So you would think that given these results, that the issue of what the best selling mechanism is would be resolved. And in fact, there is still something more you can do. Even though these auctions all have the same average revenue, their variances are different, you can improve on this structure. And in fact, that's what Roger Myerson and John Riley and Bill Samuelson did. They showed that the optimal auction is one of these types. I would prefer a Vickery, in which the reserve price is chosen according to this formula. And obviously, this formula depends on this object f of v, and or the s of v, the survivor function. And in fact, this term at the end there is the inverse of the hazard rate, which is another term coined in the duration literature. So I often, when doing empirical work, tend to use techniques from the duration literature because the object of interest is the hazard rate. You say, well, are they appropriate? Well, what do we know about time? It's positive. What do we know about prices? They're positive. So the techniques can be used in this case without incident. Now, what are some problems with this R star? Well, the first thing is that some fraction of the time, the good goes unsold. In other words, by choosing the reserve price optimally, you are building in an inefficiency. And this inefficiency highlights the tension between expected revenue maximization on the part of the seller and allocated efficiency in the economy. So 27 minutes on the shot clock. So historically, the literature concerned with mechanism design was criticized as lacking practical value because the optimal mechanism, this R star, depended on this primitive that no one could observe, or at least not policymakers. And because this distribution evaluation was unknown, how would you calculate the optimal reserve price? And so I guess the fundamental insight was that if you impose this twin hypotheses of purposeful behavior and equilibrium, you can reverse engineer, or you can identify from the distribution of actions, the distribution of latent types. So that the first thing to realize about the structural econometrics of auctions is that it's an identification strategy, right? That there's this distribution of unobserved heterogeneity that you don't observe. You only get to see actions. And there are many ways to go from those actions to other distributions. But if you're lucky, there is a unique way that's disciplined by the purposeful behavior and equilibrium that will uniquely map the distribution of actions or link it to the distribution of types. And then once you have that, then the strategy is to reverse engineer that distribution of valuations from what you observe. And then the third step is to use that object to do comparative institutional design. Yeah, why are auctions so particularly attractive? Because oh, sorry.
So all of this hinges on the risk. All of this hinges on the risk neutrality assumption.
Under risk neutrality, yeah.
So how much does that hold in real life?
Oh, I don't know. Do you have insurance? Yeah, so do I. So yeah, no. but you know, it's a benchmark to start with. If we can't solve this problem, we're not going to study that, solve that one. Right. So, yeah. Yeah, I mean, to be successful, you're going to have to be able to pretend. Right. So most researchers are quite childlike in their personal lives because they can pretend really well. Like, let's just pretend that people aren't yelling at me while I'm trying to do research.
But like in the auto example, maybe risk and value is pretty good. You're a buyer for a car dealer, and if you lose it, it's not a big deal for you, right? So in some cases, it could be a good approximation.
Yeah, so this basically summarizes my previous point. Now, why do we need this object? Why can't we just, you know, go out and A/B test our ways to nirvana like they do at Google and Amazon? Why don't we just A/B test our way? Well, if you want to A/B test, you're going to have to be doing a lot of A/B testing because you're going to need a point for every possible alternative in the policy choice space. And that's just not going to be possible, even with 140 million people. We do this because we want the primitives of the economic model. And when we have those primitives, we can circumvent the Lucas critique that you know, where you just look at past reduced form work and say, oh, if we change this, this is what will happen. So we're doing this so that we can entertain comparative institutional design. We can not only we can examine on the bench, so to speak, what alternative methods, alternative market institutions not observed in the data, what they will deliver. So we can do it without having to A/B test our way to nirvana. So what are some issues? Well, first of all, if you're just looking at the distribution of winning bids, you're looking at the distribution of second order statistics, which isn't really what you were interested in. We're looking for the distribution of V, not the distribution of V2:n. In the presence of a reserve price, all sorts of nasty things happen. First, the set of potential, the people that show up are non-representative of the sample N in general. And so in the presence of a binding reserve price, you need to consider both the joint distribution of participation or non-participation and bidding. But it's often really difficult to find a measure of potential competition. People often remark on why I study particular environments. For example, timber sales in British Columbia or tree planting ones, because in both of those environments, I had access to big N. There are lists of the people who showed up at the auction from a bigger list. So I know both the number of people who showed up and those who potentially could show up. That's not always true. And that's kind of a problem with almost whether you can implement lots of this empirical work. So basically, we're at this point where we have a bid function beta, which is English and Vickrey, and then we have this function sigma, which is Dutch and first price sealed bid. And what you see is they're different, and they're different by this second term. And so what you'd like to know is under what conditions can you learn about V from just observing either bids or strategies. So in all of this work, there are going to be three kind of fundamental transformations: indicator ones, monotonic ones, and order statistics. So this is going to be kind of a review of that literature or something new if you haven't done it. The one I want to study first is participation. You got a sequence Vn, and the guys that show up are the ones that for whom V is greater than R. And And in this case, this sequence Pn is a binomial sequence with a mean 1 minus FR, the survivor function evaluated at R, and a variance which we know. And if we add them up, they're binomial. And the thing to realize is that M is quite different from N. It's typically less. How much less? Well, it'll depend on f of v, n, and r. But the real thing to notice is that in the early literature, it was quite common to regress the observed number of participants, little m, on winning bid, and then discover, oh gosh, the more people who showed up, the higher was the price. Well, that's not even wrong, right? I mean, of course that's going to happen. But more importantly, that result, that coefficient estimate, is severely biased because the orthogonality assumption of least squares isn't met. Right? So here are some different distributions. Imagine that f of v is uniform on 0, 1, and r is, in this case, 0.2, and there's 5 people. Well, what you see is there's lots of times where everyone shows up because the reserve price is low. As it gets higher, less so. And then, sometimes no one shows up with some probability. So this isn't just an academic curiosity. The second type of transformation is the monotonic one. And here we're going to look at sigma of v. Sigma is this upward curve markets, S equals sigma of v. And this distribution down here is f of v. And the transformation from v to s is going to change the distribution of s. And the question is, in what particular way? Well, we know that this area A, which is f of v multiplied by dv, has to equal this area B, which is f of s by ds. And once we know that, we know that we can write, we can derive what f of s is going to look like. It's going to be f of s is equal to f of v dv ds. And what we're going to substitute in for v is sigma inverse of s. And then we're going to take the derivative of that sigma, because it's a monotonic function, it's sigma prime. And so we can derive the distribution of this transformation. And in particular, this distribution here, relatively straightforward. One of the things to note is that even though the support of v may be from v lower bar to v upper bar, the support of s is going to be much less. And that just illustrates this point here, where, further back than I thought, at v bar, the Dutch auction, you don't bid your time. Okay, well, now we know what the distribution of f of s looks like. What's pretty compelling about this is that the s bar depends on n and f. And why fixate on the fact that this s bar depends on f of v? Well, it violates one of the regularity conditions that Whitney assumed on day one. So this is the generalization. Imagine you have a uniform random variable on the interval 0 to theta, and you're trying to estimate theta. Take that density, which is 1 over theta, take its power to the teeth, and now take the logarithm, and now differentiate. And what you'll find is you get an estimate of 0. But 0 could mean you never observed the data, so you need to solve this problem in a different way. So what happens in this situation is that there's some non-standard econometrics. In any case, if you want to find sigma v, it looks like this hideous expression. And then when you put it in here, it looks like this, which isn't any help really. It's useful to calculate things, but that's it. So the key thing here is sigma inverse. And historically, I just brute force calculated it until Gare, Perrine, and Vong in a path-breaking paper in Econometrica noted that you can take the first order condition of expected profit maximization and write it as this ODE, one of the simplest ODEs that you can solve in the world. And once you notice that f of v is f of s of sigma of inverse, and this is true, then what do you discover? Oh my gosh, you can write you can calculate any v if you know f of s and little f of s and n. So this is a constructive way of deriving the inverse function sigma inverse of s. It's also the way that people demonstrate identification. If I know f naught of s, so I know big F of s in the top there and little f of s in the bottom, I have the unique function of s, sigma inverse, and so I have identified f naught of v, and that's the identification strategy referred to as GPV. Okay, now what's the the last kind of transformation? Order statistics, and here there's kind of several we might be interested in. And so rather than go through all of them, I'm just going to do one in particular. I'm going to say, let's consider the kth order statistic, call it x. What has to happen for x to lie in an interval x to x plus delta x? Well, I need to have n minus k, these little creatures below me, k minus one of these creatures above me, and one in that little interval. And how can that be solved? Using this combinatoric formula, right? And then what do? Well, I take the limit as delta x goes to 0, and we get the density, and there you go. Looks like that. One convenient way that we're going to use later to represent this cumulative is using the incomplete beta function, which is this creature over here. And what do we know about that function is it's monotonic. Okay, so we've got all of the pieces. We can now plug in 1 for k to get the distribution of the max, and 2 for k to get the distribution of the second order statistic. And there you go. There's the distributions. And as you can see, they're located at different points or centered about different points. These are for Weibull ones. So this is a random draw. This is the second highest one, and this is the highest one. These are for probably 9 or 5. So if you really want to derive the distribution of the winning bid at a Dutch auction, here you go. It's right here at the bottom. And you can solve that relatively straightforwardly because I did right here. And that's what the distribution of the winning bid looks like. So obviously at the English auction or at the Victory auction, there's much more variation in the winning bid. Whereas there's very little variation in the winning bid at a first price sealed bid auction. And so if you're running, you need money for public expenditures and you don't like a lot of variation, you're going to like that first price sealed bid auction because it's very concentrated. Note too that it has positive support at the upper bound. It just stops there, midair. It's not, and this is not just this example. This is a general property. Okay, so what happens? Let's derive what happens to, what the density will look like at an English auction with a binding reserve price. Well, with some probability f to the n, you're going to have 0. It's going to go unsold. With some probability n times f times 1 minus f, you're going to get a mass, a point mass at the reserve price. And then you're going to get the second order statistic. So that the discrete, or in the presence of a reserve price, the winning bid distribution is quite curious. It's a discrete continuous PMF PDF. So the two implications are that auction formats and pricing rules imply very different shapes for the distribution of bids, the winning ones in particular. And since the objects of interest in the calculation of the optimum reserve price are the PDF and CDF, methods that recover those objects are particularly attractive. And so in particular, the method of maximum likelihood. Let's do the simple example. Now we've got some data. Let's do the simplest one possible. This is why economists like victory auctions. Suppose there's no reserve price and there's NT potential bidders. The distribution of bids that you get is the distribution of valuations. So you're done, right? Just look at the distribution of bids and you've got the distribution of valuations. So two things to note. One can identify F naught of V, F naught of B, the distribution of actions. And you can estimate the distribution of valuations non-parametrically using your favorite kernel and an appropriate bandwidth, just like that. You're done. So that's kind of heartening. Now what? Let's put in a reserve price. What's going to happen? Well, MT people are going to show up and they're going to bid that trailing point. And then, NP minus M are not going to show, are going to be absent. And well, that's a bit of a problem because you can really now only identify F naught of V from F naught of B above R. So they're, depending on how big R, there's a big point of mass that you just can't say anything about little f of V. And you say, well, that's too bad. Life will go on. Well, what if that's where the optimal reserve price is? You're essentially going to have to make up numbers. So without some additional assumptions, you can only estimate F naught of V non-parametrically above R. Something also happens in the neighborhood of R is that those non-parametric estimates are severely biased. Right? And so that's a bit of a problem. So bias is going to bite you. And it's not the kind of order 1/n bias that you can jackknife or bootstrap yourself out of. This is just like bad bias. Okay, let's try some unobserved heterogeneity. If you've got a sample of observations, then how can you deal with the fact that these may differ in some unobserved way? Well, first of all, you have to take a position on that unobservedness, and I'm going to say it's epsilon, just for notational convenience. And it has to either enter additively or multiplicatively. If it does, you live a charmed life, because you can take the observed y, which is v plus epsilon, and you can find its characteristic function. Notice that it's the product of v and epsilon. Now, if you take the difference between any random pairs n and m of v, that epsilon is going to cancel out, and the characteristic function of something you can calculate is then the square of the characteristic function. You can take its square root and invert it, and you're golden. So unobserved heterogeneity is not as big a problem, provided that what? Well, there's no reserve price. Because once there's a reserve price, what are you going to do about that tail probability? Not much. So you're either going to have to take a position on the distribution of unobserved heterogeneity, so parametric like Gaussian, or something else. Now let's look at an English auction, no reserve. Well, we know that the distribution of the winning bid is related to this formula, this incomplete gamma. It's a known function. And so if we know F naught of W, we know F naught of V because that sigma inverse function is known. We can estimate F of W this as this indicator function or smooth it, and then we can invert it to get F of V, and we're done. What about first price sealed bid auctions? Well, let's do the simple case. N doesn't vary and there's no R. Well, we know from Gare, Perrine, and Vong that we can use, if we estimate F of S and little f of S, we can build these pseudo values, and then from those pseudo values, we can kernel smooth them and we're good to go. There's some issues at the top end, the S bar, because of the boundary, but typically you don't worry too much about being paid too much. What about a reserve price? Well, we're back in a heap and help and a hurt. So what happens when N and T vary? Well, it depends on how much data you have, really. You know, if you have lots of data, then you can estimate F hat for every N and then pool them. And then what happens if R varies? Oh, we're back to hurting. And we can do this with the reserve price in an English auction. So inexorably, what am I driving you to? When N and T vary across auctions, only parts of the distributions are identified non-parametrically. And so, and in the presence of observed covariates, such as of some vector xt, you're not going to be able to implement non-parametric methods with any reliability. So what do? It's what old guys and I did, like me, always do. We make an assumption about FV. It's got some parameter. We imagine things are a single index. We collect them into theta, and then we maximize the function. What does all of this have to do with dynamics? Because, you know, apparently this is the dynamic structural econometrics conference. Well, this is the building block of any dynamic model. If you want to make this dynamic, I would try crafting upon the IPV a Poisson process. Why a Poisson process? It has nice memoryless properties. It keeps everything symmetric as the game proceeds. And otherwise, you're just going to be computing all the time. If you want to talk about learning, well, there's no role for learning in the IPV. So you have to go to this affiliated model of Milgram and Weber. But the shot clock is full. So I have to hand off to my co-author and friend, John.
Thank you. Thank you. Okay, let's see if I can switch slides here and I'll put my phone here. Oh, I can put this on. Can I use your
Beautiful. Okay, 16th. Yeah, all right. So we played this auction game yesterday, but for those of you who are just joining, let's just review. We're looking at Korean car auctions, 2-minute internet auctions under these rules that limit the information the bidders. The bidder can only see their own bid. They know their own history of bids. They don't know how many other bidders, and they only see like a little light on the screen if they're the high bidder. When someone outbids them, they don't know how much they outbid them. The light goes off and they know they're not the high bidder. And we played this game against some robots. And I said, these are dynamic programming robots that we built, and we structurally estimated it from the actual data. And I'm going to try to tell you about that today. Okay. So we're going to just go over, for those people who weren't here, were online and weren't here. Let's just show you a picture. These are some pictures we showed yesterday. The red line is the high bid track, and what you see, like these blue stars, you would never see this in a traditional English auction, right? Because it wouldn't make sense to bid below the highest bid. It'd just be ridiculous. But in this auction, it makes sense because the blue person doesn't know what it is, so they make a guess and they bid this, and then they realize, hey, we're still not at the highest bid, and they're creeping, right? They're trying to find out what the highest bid, and then once they get up there, they stop, just like we did, right? And now here's an auction. So you see a lot of bid creeping in these, and you see a lot of early bidding, right? Early bidding, sometimes in 20 seconds in the auction. We also see bid sniping. We showed this one here, a bidder, the red dot, that's bidder 3, comes in at second 118 and just makes one bid and wins. Okay, so that's bid sniping. And then we see something that's kind of crazy. Here's this bidder, bidder 28, and he comes in at 1 second, 1.265 seconds in the auction. They bid 14,690. And look at all these people below. They're furiously trying to find out what the highest, and they're frustrated. They're bidding, and there's somebody that just bid way above them, but it looks crazy for this person to do. Why bid so early? If they would have tried to learn themselves, they may have this huge value. They could have bought this thing for much less, it looks like, right? It looks stupid, right? What they're doing. And then Harry mentioned some crazy bidding. Here's this non-monotonic, this blue square, bids up and down and up and down. According to the auction rule, it doesn't matter. You are obligated to the highest bid, and you lower it, doesn't do anything. And it doesn't even show up to the other bidder. So there's no purpose for this, right? It's harmless in some sense, but this is stuff we see. Yeah, question.
The auction from a couple slides ago, when you have that one guy that just came in at the very end. Yeah. Is there some intuition for how he's able to literally just guess the right price versus some crazily high number? That seems.
No, I mean they have, unless you think there's colluding or something, but they don't know what's going on in the auction. There could be people who are outside the collusive ring, so it may be just by luck he came in at that last instant and had a slightly higher bid. But he's just slightly higher than the diamond, who is a little bit after them, right? The pink diamond.
Yeah, I guess it's just fact. He's literally just has an optimal bid to win at that point at the very end when he doesn't have any information.
Yeah.
The auction. It seems really strange, I guess.
So we see the behavior. Let's just think about the theory. And see, this auction design, actually, Bob Miller has a paper in the Journal of Econometrics for Texas CD auctions, and they have the same rules, right, for Texas CDs. And he's got an analysis. So I would strongly recommend reading that paper. And Bob modeled it the way you want to model it. He's saying these bidders are bidding a perfect Bayesian equilibrium, all right? And so Ariel Pecos will be talking about dynamic game theory. But what is so it's a dynamic game of incomplete information, but it's more difficult than the IID extreme value incomplete information we've been talking about earlier, those shocks, because they're transitory. But your value is persistent, and you want to learn your value. And that doesn't change from second to second. So you have to, as a Bayesian, you're trying to learn and infer from the bids, trying to invert them and figure out the values of your competing bidders to know what to bid yourself. That's a devilishly hard problem that nobody solves. Even in a open ascending bid, like a double auction, nobody's been able to solve that yet. We don't know how to solve that, okay? Now, and so you might say, we're going to a second best. We're going to say, this is too hard for us. We think it's actually too hard for most people. And here's what we think if people were smart enough to solve this perfect Bayesian equilibrium, we conjecture there'd be no early bidding. Everyone would snipe. Essentially, the mind game of perfect Bayesian yield, everyone realized it's to my disadvantage to bid early. Bidding early is going to hurt me. So everyone's going to agree that we bid right at the last instant. And then this Korean auction becomes strategically equivalent to a static sealed bid first price auction. Yeah.
That's the unique PV.
Well, we think so. So let's just give you an example. Let's go through this now. We're going to do a two-period, this is conjecture on our part. So I'm going to script through these slides and just go through this thing. So, perfect Bayesian equilibrium, it's a Markov perfect equilibrium, but the state variables now are your beliefs that follow Bayes' rule. And, Ariel will talk about it more generally, but you're going to use Bayes' rule wherever possible. But there's some issues about off the equilibrium. You want to have a complete decision rule under every possible contingency. And sometimes you might see a zero, what happens when you see a zero probability event that, couldn't have occurred according to your prior. So I don't want to get into all of these here, but I want to just go into immediately this example, this 2x2 example. So there's two bidders, two time periods. There's a bid period 1 and period 2. They both have uniform distributions. Now we're going to call the informative equilibrium. The uninformative is when they both snipe. They go to the last period. If they wait to the last period, we know that's what Harry talked about today. That's the first price sealed bid auction. And there's a closed form solution to that. You can solve that. But in the first period, now we want to think about backward induction. If you were to bid in the first period, we call that the informative equilibrium, because by putting themselves out there, they're revealing some information. And what do they learn in this Korean auction? What you learn is only whether you're the high bidder or you're the low bidder. You know your bid, but you learn whether you're the high bidder or not. Now, what that does is the auction might be ex ante symmetric, but in the first period, this information makes it asymmetric. In other words, someone knows the high bidder and the other knows the low bidder. Let's show you a picture. There's some mathematics here, but this is the period 2 equilibrium where H is, I know of the high bidder and I'm low bidder. And these things differ because the distribution of valuations, depending on whether you're the high bidder or low bidder, change according to these formulas. So if you're a high bidder, we're going to show that you bid less aggressively. Let me show you a picture here. This is better than the math. The black line is in the second period. If you just played the sniping equilibrium, they would bid 1/2 of their valuation. That's the symmetric equilibrium. Yeah.
Yeah, so how much does the assumption that the other players know there is 2 players do here? Because say you in the first period just send in 1 Conrad, then you can see if you can kind of maybe infer how many people are playing or something like that.
Yeah. We don't know. The answer is we don't know. We're assuming there's 2, and that's known. But in the actual auction we talked about, you don't know how many. You could actually only be 1 bidder. You could actually play an auction only against yourself and never realize it and just be bidding against yourself. Yes.
So how do you think about equilibrium selection in these models, right? Like we want people to not collude, but we also want them to within 2 minutes learn that we're all playing the same equilibrium.
Yeah.
So
that's over my pay grade here. Equilibrium selection. Fedor is going to be talking about games with multiple equilibrium. How do you select equilibrium? We don't really know. We assume that the players select that equilibrium somehow through coordination, some kind of coordination mechanism. We don't know. And we don't know yet whether this Korean auction has multiple equilibrium, or what we can show is the sniping equilibrium is always an equilibrium. That's always, if you think about it, that's always one equilibrium. The question is it the only equilibrium, or there are these other informative equilibria? Now, in this example with known 2 bidders, 2 periods, we're going to answer, the answer is no, there's no informative equilibrium, because in the first period, if you bid, if you were the low valuation, you're going to bid more aggressively in the second period. You say, I'm a low bidder. To win, I have to go bid higher. I'm going to have to outbid the high valuation. The high valuation is the blue line. They can lay back and not bid as aggressively. But the point is, both of those lines, the red line and the blue line, lay above the black line. So this is how the informative equilibrium unravels. Each bidder realizes, suppose, one bidder says, why should I bid? I'll let the other guy bid. They will think they are the high bidder and they'll bid against the blue line. I'd rather bid against the blue line in period 2 than against the red line. So if they both think about that, the equilibrium is going to totally unravel and they're just not going to bid in the first period, and there'll be a unique sniping equilibrium, non-informative equilibrium, which is the first price sealed bid auction, equivalent to a static sealed bid auction. So that's our argument why a perfect Bayesian equilibrium doesn't exist. It's informative. Now, Bob might have a different view. We don't know. This is to prove this in general with random numbers of bidders and everything, that was a high task for theorists to do, right? So we're just throwing it out there. Yeah.
I agree entirely, given that there's no cost of sort of coming in earlier or later. And in a 2-minute auction, that certainly makes sense, that there's just no cost. And so you can bid whenever you like. And I think that you can establish uniqueness, that there will, I think your result establishes uniqueness, because we found the same result. But if there's no cost, there's going to be a sniping equilibrium at the end of story. So the way we got around that was to say these guys have opportunity cost for their time. And so there are these other reasons why people might come in early or later. And that's why you might get these high bids early on, because these guys, bank managers in our case, as opposed to just car buyers, hundreds of thousands of dollars, they may be making one bid and exiting because they got other business to do. But you need something else in order to get people to bid early. Yeah. And that's what we have in our framework.
But Nico.
So two pieces of intuition for this in my view.
Yeah.
One is that things like affiliation might create some reason for bidding early, because there's some value in getting information about whether other people are also high bidders about. And the second thing is, it seems like the conditional distribution of the tail behavior, or the conditional distribution of knowing whether the high bidder or the low bidder. This is uniform, I assume?
Yeah, uniform, yeah.
So that could also make a difference on whether you bid more aggressively or less aggressively if you go the higher.
Okay, that we'll have to follow that up. That's an interesting point. Yeah. So, but the point is right now is we have a paradox of rationality. We not only we can't solve these, but we think they're not really this informative equilibrium doesn't exist. And we look at the real data, we see tons of early bidding, but we also see most of the bidding is at the last minute. So here's a CDF of when the winning bid is submitted, and there is early bidding, but the real heat is in the last few seconds of the auction. Okay, so it's like no individual bidder of the 90 bidders in all these auctions that are identified will ever always snipe. Sometimes they do snipe, but it's actually uncommon. Even among the people snipe, they don't always snipe. They often bid in the middle of the auction. Okay, and then there's delay. The fraction, the no bid submitted yet. You can look at the median it's like within 10 seconds. So there's often no bidding within the first 10 seconds of the auction. So there's some delay. Yeah.
And so here again, we're seeing a difference between your empirical application, the one that we looked at, because although we get some sniping, only about 30% could be attributed to sniping at the end. There's quite a lot of winning bids submitted before just halfway through the auction, which incidentally lasts an hour.
An hour, yeah. Yeah, interesting. Yeah, we definitely have to compare. So, this is now, the interesting part of where I've been going in structural econometrics is we're backing away from full rationality, but we don't want to make the people stupid. There's actually a guy at Yale named Shyam Sundar, and he's got called Zero Intelligence Traders. And in the double auction, these are like really stupid traders, but he showed that collectively you put in a double auction, a dynamic double auction, they're just bidding randomly, below their valuation, so that they don't lose any money, but they just completely IID random bidders and totally stupid. But a collection of these, they converge to equilibrium, right? So that's the agent-based way. But we want to be somewhere where we want to make them smart, but not so smart that we can't we can't solve them ourselves. And so, that's what we're trying to do here. So let's just outline a model. Given the time, how much time do I have? Like 20 minutes or something? 15 minutes? 15 minutes. Okay, I don't want to go over time. We'd like to take game theory seriously and test it whenever possible. We just don't know about this perfect Bayesian equilibrium. So what I'm going to use is a dynamic programming model. The agents are going to be smart to use dynamic programming, but their beliefs are going to come from rational expectations. Okay, so we're going to assume these guys are very experienced bidders, and they are. They participate in thousands of these auctions, and their beliefs are pretty fixed. In other words, they're not going to have to use Bayes' rule. They kind of know how high, they know the bid tracks on an average, and on these cars, they know the distribution. And when they know it, they have all this experience. And so we're going to basically endow all these people with the same conditional probability of beliefs about how high they'd have to bid to be the winning bidder in the auction. It'll be a probability distribution that shifts during the auctions. Okay. And then once we have those beliefs, we're going to use dynamic programming. But it's going to be not enough. We're going to have to add some other behavioral shocks. We're going to have to add some extreme value error terms, some noise, and we're going to have to add some, we're going to have to borrow from Chris Sims, and we're going to have to actually have a model of rational inattention. We're going to assume in this 2 minute, when we played this, I was including delays, but 2 minutes really fast. And even typing in a 4-digit number takes almost a second if you want to do it carefully. And so, at the time they're looking at their cell phone, someone's talking to them, and then they're looking at the auction. So we think it's very plausible that any given second, they're distracted, they're not paying attention. And so we're going to call that rational inattention. They're just, with some probability, they're not looking at their screen, and then they come back later, and then they have attention, they type in a number and decide to make a bid. So we're going to have these features of quasi-behavioral with dynamic programming to say, if we put these in together, can we explain the early bidding? And will these guys be pretty smart bidders, but also be like the people we see? And the answer is we're going to say yes. Okay. Now, basically we're saying because of a lot of experience, these guys have fixed beliefs that we're estimating from the data. And we're going to focus to make the beliefs even more homogeneous. We're looking at just these cars, 533 auctions for these standard Hyundai Elantra cars. We picked them out of our 11,000 auctions. And out of these 533 auctions, there's an average of about 8 bidders. So we have 4,029 bidder auction pairs in our data set. So we see, it's like panel data. For each bidder, we see during the 2 minutes what they do in each auction. And then we're going to basically use a fixed effects approach to estimate 4 parameters for every bidder in every auction. And one of them is what Harry was talking about, the valuation. We're going to try to estimate their value for one of these cars. And that's going to be one of the parameters we're going to estimate in every auction. Then recover the distribution of valuations, and then try to do mechanism design or market design. So here's an example of the unconditional beliefs. If you haven't bid at all in the auction and you just were thinking, depending on the first second, that's the bidding there. And what you get is a pattern of beautiful stochastic dominance. At the very last second, 120, this is the distribution of from the data of what is the highest bid in the auction. So that's the bid you would leave. So in each second, you're on one of these lines. If you hadn't bidden yet, you're going to have believe that this is the distribution of valuation at that second in the auction. Now, if you did already bid, then there's 2 possibilities. You were the high bidder or not the low bidder. There's also going to be bids there. If you bid, this is if you've not bid so far. Once this is the no information yet. I haven't bid. Once I bid, then I put a bid on the table and I learn either I'm the high bidder or I'm the low bidder. And then there'll be other bidders that we can estimate, essentially non-parametrically from the data. So these beliefs, everyone has the same beliefs. I want to emphasize in this model. And here's how it works out. Here's a bidder in auction 9810, bidder 23. Here's the high bid track, which they don't know. And this represents the expected value with these beliefs. And they're going up. See, it's off the chart. There are beliefs below here. We just, cut this off here. But they're ex ante beliefs. They haven't bid yet. But as time goes on, they know that the bidding is going up. So the mean bid of what it needs to be the winning bid is going up. And then look at it, jumps up because they bid that star, and then they realize they're not the high bid. So then their new bid jumps up. And then see how it comes down? Once the star hits the high bid, then they realize, oh, if they weren't the high bid, they might have thought it was the highest bid was a lot higher. But once they have the high bid, their beliefs collapse. They say, oh, I have the high bid now. And for a little bit of time, their belief is exactly their high bid. But then somebody outbids them, and then it jumps up again. So these actually can look plausible. They don't look crazy, the kind of beliefs. So now we have beliefs that are complete beliefs under any contingency in the auction, given what they experience. And here's another bidder 23. So now let's think about the dynamic programming problem. So we're going to have a two-step estimation. We estimate the beliefs in step one, and they're fixed. Everybody has the same beliefs. And then in step two, we have these structural parameters. Every bidder has 4 parameters. V, the valuation for that car. C, there's going to be a cost of bidding. P is the inattention probability. And sigma is the extreme value scale parameter for the sigma extreme value shocks. And we're going to then estimate. You think about these as fixed effects for every bidder in every auction. So we have 4,029 bidder auction pairs and 4 parameters. So we're going to be estimating 16,000 parameters. And I did that this week. We did that this week. And how do we do that? Well, we use parallel processing, and we had a different core running for every structural estimation. It was round robin. And so you're seeing results that are straight off, hot off the computer. So I want to put a big caveat. We haven't totally bug checked this in it yet, but so far I'll show you some numbers. They seem to make a lot of sense. Now, to go into the whole dynamic program, I won't completely be able to show this to you, but let me show you a Bellman equation. So let's look at the terminal WT at t+1. That's at 121 seconds, the winner is revealed. And if your bid was BT +1, that was your highest bid at 121 seconds revealed. And HT is the indicator where you're the high bidder. Well, if that's 1, you won the auction. And if your valuation is V minus, that's your profit, right? So that's the terminal payoff. And now we have this conditional belief, Lambda, which is at the last time instant, I have at 120 seconds, it's the last chance to bid. If my highest bid was BT, and either I'm a high bid or not, I have this belief about the winning bid in the very last second of the auction. So then I can go backward induction, and I can say, at second 120, I want to choose a bid to maximize V minus B times the probability I win. Okay, that's very like the static auction that Harry just showed you, right? Static first price auction. That's a sub problem of this. And now we work backwards. Now at time T, there'll be some epsilon shocks. There's going to be this epsilon extreme value to either not bid at 120, or I could bid at 120. And if I bid, I can bid any continuous value bigger than my current bid. But then there's a cost. There's a cost to bidding and a shock to bidding. And there's a scale parameter for this. And so there's an extreme value, a randomness about whether I actually bid there. If I shut down this and this, you're going to almost always bid in every second of the auction. And that's too much bidding. So we're putting in bidding frictions to prevent too much bidding. We get early bidding, but we want to have too much bidding because that's not consistent with the data. And then in addition, we have the Chris Sims inattention parameter. It's just like maybe as a second 120, someone say, hey, John, or, hey, Sungjin. And then you look away, and then suddenly you look back at the screen, oh, auction's over. So we have these things. So You get the idea that we do backward induction, and then we can form a likelihood. So now we can define a likelihood, a conditional probability of bid, given the history over the 120 seconds in the auction. And here's our friend, the logic choice probability, right? That we talked about, Bertel, and talked about yesterday. And now, here we just have, we can discretize the bids. So any bid prime, because bids are naturally integer. If you look at this auction, they're not bidding 5,200.22. They're bidding to actually the nearest 10 most of the case. So oftentimes the nearest 100. So we could just define a lattice of integers, and then we could approximate the continuous bidding problem as a discrete choice. Now, what we did is actually we call quasi-maximum likelihood is the first. We eventually intend to do this. But this is kind of a little more computationally intensive because I have to evaluate this value function at every time and all possible bids on this grid for all possible bids. It could go from, 0 to, 15,000. That's a lot of evaluations. I can, there's some tricks we have. I won't talk about it now. But what we found is that this quasi problem is what we assume is we're just going to choose the max, and we have MATLAB has a program called fmin search, one-dimensional search, and instead of valuing all of these, it does a polynomial approximation of this function, and in 15 or 20 evaluations, it only needs 50 to maximize this, and it gets it pretty well. So this is just faster. So we started out with this. Now what this assumes then is when the person does bid, they're going to bid optimally on this function, the bid. Now, the question is how accurate is that? Can this model accurately predict the dynamic bids when they make bids? So let me jump. I have 2 minutes left. Let me show you a fit of this model. Here's a bunch of details on the likelihood and stuff like that. And these are parameter estimates, but here's a figure I like. So this is auction 10,007. This is bidder 10, and the dotted line. So this bidder did not bid until those last 4 stars. And in the auction, the dotted line is for the maximum likelihood estimates for this bidder, and their values. We estimate the value of 55, 66, an inattention probability of 98.5%, a cost of bidding of 1.26, and a sigma of 0.52. And for that model, the model predicts the dotted line is what he should optimally bid if he were to bid, if he wasn't distracted. So in this model, the model is predicting, wow, he's distracted a lot of time, but then here he's not distracted toward the end of the auction, and he bids there. The model's just kind of nailing it. And then he bids another one. It's kind of almost nailing every one of his bids dynamically as he's ascending his bid in the auction. And it's not just, I'm not just cherry picking this. I'm going to show you another bidder. This is bidder 11. This is bidder 16, who makes only one bid. And here is bidder 23, who's the winner. Now here we see a little bit, they're a little bit below the optimal bid, but pretty close. Okay. Now let me just conclude. These figures show the conditional win probability for this bidder 23. They start out very pessimistic. We showed this is the beliefs about winning the auction. It follows a martingale. And then what happens is that toward the end of the auction, when they realize his beliefs really change. So at the beginning, he's not bidding, and so nothing's changing his beliefs. But then later, when he starts bid, you see this. He's going up and down in his beliefs, but very pessimistic. But then suddenly, toward the end, he says, "Hey, I'm going to win," and bam. And then the red line is the probability. If he's not distracted, that's the probability he's going to bid. And then this line here, the red line shows the expected payoff if he bids, and the blue line is what if he doesn't bid. He just holds his bid. So there's generally a very big gap, a big gain to bidding if you can. So let me just conclude then that we get these expected profits of the auction winner. It's a distribution of profits, And we don't know the answer yet, but this is, sniping is a sub-strategy. In other words, it's a suboptimal. Generally, you want to learn early, but if you were to wait to the last minute in the auction, what would you bid? Okay, so, or if you were constrained to only bid at the last second, you could, or you should only just make a sealed bid auction. We calculate what that bid is, and then we compare the winning bid to the sniping bid. And what we find actually is a positive distribution. In other words, there must, I won't call it animal spirits because these are like Dr. Spock, they have no emotions. But something in the frenzy of the bidding bids up in the dynamic bid, leads them to bid higher than they would bid in a sealed bid auction. So it looks like maybe this Korean auction designer was smart. We don't know yet. We're still thinking about that. But this would tend to say that this dynamic auction actually is leading to higher bids than a static auction would be. So I'll stop there.